Welcome back to the channel. Today we're going to talk about Automotive Electrostatic Discharge, or ESD. Now, ESD is a type of a spark that occurs when there is a potential difference between two objects, and one object is carrying charge and the other object has a direct path to ground for it to receive this charge. So then, when they get in contact with each other, the ESD transfers from the object A to the object B, and basically on its way to ground can destroy some sensitive electronics. Now, when we talk about automotive environment, the things become a bit complicated because, as you probably noticed, vehicles have tires that actually made of rubber and not really conductive very much or at all. So how can a vehicle receive charge? Now, this question may seem simple, but really it isn't. And as I discussed in my previous video on the topic of automotive EMC, the United Nations Regulation 10, which is the global standard for EMC in vehicles, does not actually require ESD testing at all. Because, as a matter of fact, it considers that a vehicle is unlikely to suffer from electrostatic discharge. Now, is this really the case? Think about the situation when somebody enters the vehicle, and if they happen to carry charge because they're wearing perhaps a wool sweater and it's very cold outside, so as they get into the vehicle, obviously they're gonna touch it. And in what places they would touch it? They may touch the wheel, they may touch the CD player, or they may touch the ignition switch. All of these locations actually happen to be likely to receive ESD in this case because as the person getting into the vehicle touches these objects, there may be a potential difference between the vehicle and the person, so there will be an ESD. Having said that, in this situation, when a person is getting into the vehicle or getting out of the vehicle is stationary. Therefore, it is extremely unlikely to crash in the event of electrostatic discharge causing some damage to internal electronics. And this is my best guess as per why ESD is not part of the scope of the UN 10 regulation. If anyone has any better ideas, please let me know in the comments. Now, when we're talking about passing criteria of the device, there are several levels, and typically for very high voltage spikes of up to 15 kilovolt contact and 25 kilovolt air, you would just expect the performance criteria D, which means that the device reboots and basically requires a restart, and then you can continue operating as normal, so it doesn't sustain any permanent damage. Now, there are other criteria for lower test cases at 4 kilovolts, which means that the device just carries on as usual, doesn't really glitch, and that would be the performance criteria A. Then if it does glitch but does not disrupt its normal function, then that would be the performance criteria B. And finally, if it's bad enough that the device resets itself, that would be the performance criteria C. So it's A, B, C, and D. Those are the performance criteria that we're looking for. So now we are ready to begin the test or start preparing for it. So the first thing that I have here is the metal plate below the device under test. Now, if I were doing this test according to the test standard, I would also have a vertical coupling plane, but I do not have that. So I only have horizontal coupling plane. And very important, I have grounded this plane into the building by connecting this lead basically into the socket. You want to make sure it's switched, right? And similarly, now we also need to make sure that our ESD apparatus that generates the spike is also grounded, and that is done with this earth lead that comes from the ESD gun itself. So it's very important to double check that both of those connections are present, otherwise you will be risking making wrong tests, so doing the test wrongly, getting wrong results, or even injuring yourself. So I have checked the earth connections, and the earth connections look good, so now I can switch on the equipment. When we turn on the test set, we'll see that it's been powered on, but we'll also see that the interlocks are now open, and it's very important to, with this one, to make sure that these connectors are actually plugged in, otherwise it won't work. So that's something that I often forget about. Then once it's ready, you can click the interlock reset button, and now it can really begin. So with the device itself, I'm trying to find the best position. We can set first of all the test based on the tip that we're using. You can't see that. So this is the contact discharge. So that means that the tip is conductive and you're going to touch the surface that is also conductive. Now we also have another tip which looks like this, and this is the air discharge. So you would typically apply this tip for testing something like a glass display, as you will see in a few minutes. Now we have the contact discharge at the moment, so I'm going to set the test accordingly. And we can choose a standard. So the standard that we're going to follow for automotive is ISO 10605. Now there is another standard for residential and commercial environments, which is the EN 61000-4-2. With regard to the way that the testing is performed, there's actually very little difference between the automotive test standard ISO 10605 and the commercial/residential test standard EN 61000-4-2. The main difference is that the ISO standard goes beyond the commercial and residential test levels and goes up to 15 kilovolt direct and 25 kilovolt air, as I described previously. So we're going to select ISO, and I always go with the default probes, but you have a couple of options here, so you can see where it's applying. So we're going to go with a second option because we're testing electric equipment inside the vehicle, not outside. Then we're going to pick the lowest resistance, and finally we get to the actual voltage. So we typically going to start with 4 kilovolt. I'm not sure why 2 kilovolt is listed, but it's not necessary. And then you can see that it goes up to 15 kilovolt. Actually, the test allows you to do even more, but for contact, we don't have to do more than 15 kilovolt. So we're going to start with 4 kilovolt. Now you can see that the basically settings. The next thing to do is, once we selected 330 ohm resistance of the probe, we need to actually apply this module from the box of tools, which is the network module as it's called, and that goes in here for this device. Here you go. The first thing that's going to happen once you've done that is that the device will begin calibration. So it does it automatically, and you should just wait for it, really. So during this process, the device is internally calibrating itself for this probe. Now, as I was saying, there are several other options available. So this is the network module with a 2 kilo ohm tip resistance, and this is the network module with 150 picofarad tip capacitance and 2 kilo ohm tip resistance. Now we are finally ready and we can begin the test. The first thing to do is to apply the contact discharge into the coupling plane to check that it works. Okay. We can also adjust the settings of how we apply the discharge. For example, I like to use press to start and release to stop. Yeah, you can probably you can't hear it, but it is discharging. So as you can see, the device actually not affected. Maybe you cannot see, but yeah, you can see when I tip it over that the device is not affected by the discharge into the coupling plane, which is a good sign. And it is also discharging, which means that the device is actually coupling into the main screen. So at first we apply X amount of pulses as prescribed by standard into the coupling plane. If you have a vertical coupling plane, you will do the same. So now I'm going to increase the test voltage for the coupling plane to 15 kilovolts. At the moment I was using just 4 kilovolts. Make sure to always use exactly the right tip characteristics that you're actually using. And now I'm selecting 15 kilovolts. So if you look at it like this on a screen, you can see the tip capacitance and tip resistance and the voltage selected. And also the discharge time is as per the ISO 10605 standard. So now I'm going to discharge it holding my hand into the coupling plane. Yeah, see, now is a big sparks going. You can see probably even from here there is coupling. But as you can see, the device is actually not affected by me discharging 15 kilovolts into the coupling plane. So, so far this is the performance criteria A. And we're not going to do air discharge into the coupling plane because obviously it's metal, so you use contact discharge. Now that I satisfied myself with the discharging ESD into the coupling plane, I'm going to set my voltage back to 4 kV and do contact discharge on the DUT itself. When we apply contact discharge to the DUT, we need to find the points where it can actually be applied. Now, with this being glass screen, we don't really want to touch that, so actually there isn't really much points on the front, so I'll have to shift it a bit sideways so that I can still see it. Okay, to allow me to do that, I have mounted DUT into these bubble wraps so that now I can actually access the conductive surface of the DUT, which is on the back, and I'm going to apply the 4 kilovolt contact discharge into it, whilst also looking at the monitor so that I see what's happening. So I'm not going to record this on my camera because this is impossible. And all that I'm doing is that I'm applying discharge into different points on the DUT where it can actually discharge into, which is the contact discharge. Okay, so that is quite happy. I can swap the polarity to negative and do that again. So technically you're supposed to do X amount of pulses on positive and negative polarities. Once again, nothing is really happening, which is good. So this is the performance criteria A. And now I'm going to change the voltage level to 8 kilovolts. So I'm going to double it from 4 kilovolt to 8 kilovolt. And I'm going to repeat the test. So this is still contact discharge. You can hear it clicking, right? There's nothing happening. I'm just making noises to make it exciting. But really the device is handling 8 kilovolt just as good as it did 4 kilovolt. So now I'm going to go to positive polarity and repeat the test at 8 kilovolt contact discharge level. That was a big. Okay, nothing's happening still. Oh, the device actually turned off. So now if it restarts itself, I'm going to count it as a performance criteria D. Sorry, I meant C. So now, yeah, you can see that the device is back and basically it restarted itself without manual intervention. So that counts as a performance criteria C. So that's good. That means the test setup is working and it is acceptable at 8 kilovolt to be performance criteria C. So, but not D. I don't think so. So next we're going to do, so far we passed with the performance criteria A for 4 kilovolt contact and we passed with the performance criteria C for 8 kilovolt. Next we're going to do 15 kilovolt contact. And now we're going to look for a performance criteria D. Let me set the ESD gun again. So I've set my ESD gun and now I can apply it to the DUT. So hopefully you can see that's a big spike. Another one. So now you see it doesn't really take much effort to discharge these. However, the device still stays on and you see that it's doing and handling 15 kilovolt quite well. So now last time I applied the spike somewhere in this region when it restarted itself, but it doesn't seem to be doing this. So big spikes here. Electro Boom would love that. Yeah, the device actually remains completely unfazed. I'm not entirely sure what I managed to do at 8 kilovolt that switched it off, but it's not happening at 15 kilovolt. Now I'm going to go to negative polarity. Maybe it will happen now. Let's see. So you see the sign. Yeah, there's no issue now. You can also count the number of discharges. So I don't really have a specific number in mind. I'm just trying to go for all points. Oh, look, it did go off. So it's restarting itself again. So, okay, I was not making it up. And it actually is switching itself off once in a while when you discharge this gun at 15.8 kilovolts. It doesn't do that at 4 kilovolts. So let's see if it comes back. So we're looking, remember, for the performance criteria D. Okay, the device does not come back, so that's not encouraging. But now I'm going to restart, so that means it doesn't meet the performance criteria C anymore. So when it doesn't meet the performance criteria C, we're going to manually restart the device and see if that brings it back to its normal function, which would then be considered as a performance criteria D. So I've disconnected the power from DUT and I've waited for a few minutes for it to discharge fully inside the battery. Now I'm going to power it back and see if it comes back online. And I can see straight away that there was a red LED that did not turn on after the last time, and now it has turned on, and you heard a pop, which is the speaker. So that means that the main controller or the main MCU is now on, and most probably the device is back. So try not to disrupt it too much. Yeah, you can now see that the device came back online. So that means that we have fulfilled the criteria, the pass criteria for the performance criteria D. So as you can see, it's getting a lot harder to pass this test for the devices compared to the basic residential and domestic test levels, which are just 4 kilovolt. 15 kilovolt going up to 15 kilovolt makes a big difference. Even 8 kilovolt, we saw the performance criteria C, and now we've got the performance criteria D. And if the device were an immunity function, something that requires to be on at all times, then that would actually be a failure. But in this case, this is a pass because the device is not an immunity function. You can read more about the immunity and non-immunity functions of devices in the United Nations Regulation 10 or ECE 10, which is freely available online and applies to majority of automotive apparatus in the market, which include electronic sub-assemblies. So now that we've done the contact discharge testing, I'm going to do air discharge testing. So first of all, I'm gonna enable the interlock whilst I'm changing the probe. So that means the device now cannot discharge whilst I'm doing this. And I'm going to use the air discharge probe that I showed you earlier. Once I've done that, gonna undo the interlock, and I'm going to set my settings for 25 kilovolt air discharge. I'm going straight for the maximum level because I really don't expect it to discharge at all. It has a really thick glass protector and a very thick plastic cover, and remember, the air discharge we only apply to the areas where there's no metal, so I'm not going to apply it in the area I showed you earlier for contact discharge because well, it obviously will discharge into metal, but we're looking to see if it discharges through the plastic, and that's the point of the air discharge. So, okay, I'm selecting ISO, I'm selecting the same probes, and this time I go to 25. This is actually the maximum test level. You cannot select any more than 25 kilovolt. So we're gonna start with positive polarity, and let's see what happens. So the settings are more or less the same for the air discharge, and basically when we do that, we're just going across the display. Ooh, you can hear it crackling. But it doesn't discharge. Oh, it's hard to show. Oh, it discharged, but device has handled it. So on the back of the unit, we're just gonna go around the chassis. And you can see it, well, you probably can't, but you can hear that it doesn't actually discharge, except like very minor places. In this location, we actually might see discharge because you see the metal of the speaker is not far. Oh, and it went in and you saw it turned the device off straight away. So this is the 25 kilovolt discharge for you. It immediately basically turned off the device. Here, obviously the speaker is quite exposed, and you can easily get the air discharge into it. So this is effectively all there is to ESD testing, and we have performed ESD testing to the maximum level, which is 25 kilovolt air and 15 kilovolt contact. It doesn't really get any higher than that unless for some very specific military-like applications. So this is the worst case scenario that you are actually likely to encounter in a day-to-day EMC testing life. I hope you found this video useful and it gave you interesting insights about the applications of ESD testing and what this testing actually look like. Please like and subscribe to the channel. I'm going to make more videos like this dedicated to EMC testing and radio testing and RF and specifics. So I'll see you in the next video very soon, and since it's Christmas time, so enjoy your break and have a happy new year.